So here we go. This will be our first full-fledged example of going through the process to come up with a rough sketch of a polynomial function of a higher degree. Example 3. For the polynomial function f of x is equal to negative 1/4 times the quantity 3x plus 1 times the quantity x minus 4 all squared. Okay, I'm going to walk you through the process. The first thing we're going to do is state the degree and the leading coefficient. We're going to use that information to describe the end behavior, and then we're going to go into the zeros. So we will list each real zero and its multiplicity, and then state whether the graph crosses or touches the x-axis at each x-intercept. Then we'll find the y-intercept to get an additional point on the graph. We'll determine the maximum number of turning points, and then we'll put all the information together to draw a rough sketch of the polynomial function. Okay, so let's get started. All right, the first thing we need to do in part A is state the degree and the leading coefficient of f. Okay, so we've got our polynomial function, and the thing is, it's already factored for us. Okay, that's really good. It's actually very helpful. If you're trying to factor something like this, a polynomial of a higher degree, it can be a headache. So the good news is when you're doing these types of problems where you're graphing your polynomial function of a higher degree, the function will be given to you in factored form. Okay, now you may be concerned, you may be saying, okay, well, I've got to multiply this thing out so that I can get the degree and the leading coefficient. Not true. Don't waste your time. I'm going to show you a shortcut so that you can come up with the leading term without multiplying this whole thing out. Okay, this is what you're going to do. This is the little shortcut that keeps you from multiplying this thing all the way out. Okay, I am going to break this down. Okay, when you look at this polynomial function, it's got the negative 1/4, that's a number out front. That is multiplied by 3x plus 1, that quantity. And then the x minus 4 is squared. Okay, so I want you to break it down like we've broken things down in the past. If you square something, you multiply it by itself. So this is going to be x minus 4 times x minus 4. Okay, so that's how we're going to break this down to begin with. Okay, to come up with the leading term, and remember what the leading term is. If you were to multiply this whole thing out, what would be the piece that contains the highest power of x? Okay, that's what we're trying to come up with. Okay, to get it, this is what you're going to do. Okay, I want you to highlight or circle however you can indicate it. Everything that has an x. Okay, so the 3x. Okay, I'm going to take that. I'm going to highlight that. Not just the x, but the number that comes with it. Okay, so that's the x from this piece. Now I'm going to highlight the x from this next part. Okay, and then the x over here. Okay, if there were numbers in front, okay, like these two pieces are 1x and 1x, but if it were like a 2x, you would highlight the 2. Okay, so you're taking the x's and the numbers in front. Okay, you're also going to take the number that's out front. Okay, the negative 1/4, even though it doesn't have an x, it's in front of the whole thing, so it's going to come with us. Okay, whatever I've highlighted here, we're going to multiply together, and that's going to give us the leading term. So the leading term is going to be negative 1/4 times 3x times x times x. Okay, let's multiply the numbers together. Negative 1/4 times 3, put 3 over 1. Multiply your fractions across the top and across the bottom. That's going to give you negative 3/4. And then you've got x times x times x. That's x cubed. Okay, that's the leading term. Okay, so this is going to, if you were to multiply it out, this would be the piece containing the highest power of x. So we can make the conclusion that this is going to be a degree 3 polynomial because you have x cubed, x to the third power. The leading coefficient is going to be the number out front. It's going to be negative 3/4. Okay, so this is going to help us in part B to describe the end behavior of our polynomial, how it's acting at the endpoints. Okay, so what you can see from part A is that we have an odd degree. Okay, 3 is odd, and we have a negative leading coefficient. Okay, So if you need to, you can refer back to in behavior on page 4, okay? We have an odd degree and a negative leading coefficient, okay? So that is going to be this box over here, okay, in the bottom right, okay? Any polynomial of odd degree with a negative leading coefficient is going to behave like negative x cubed does. So it's going to rise to the left and it's going to fall to the right, okay? So let's go ahead and put that down, okay? If you need to, you can draw yourself a little sketch, okay? It's going to behave like this, okay? So I'll even write it behaves, this polynomial is going to behave like negative x cubed, okay? It rises left and it falls right. That's how we explained it in everyday English. But here I have you fill in the mathy blanks, okay? So, you know, if you're putting this in an XY plane, okay, trying to do my best to do that. Okay, so remember how you would write this down. Okay, so there's two pieces to the in behavior statement. You're first going to say what happens as your x values approach negative infinity. So if your x values get more and more negative, so if your x values are going in this direction, what's happening to their y values? They're going up, up, up in the positive y direction. So your y values will be approaching positive infinity. And then you have to make the second statement of what happens as your x values approach positive infinity. So if your x values are getting more and more positive in this direction, their y values are getting more and more negative. Okay, so their y values are approaching negative infinity. So this statement, as your x values approach negative infinity, their y values approach positive infinity. And as your x values approach positive infinity, the y values approach negative infinity. That's how you mathematically write that this polynomial function is rising left and falling right. Okay, when we get to part F, where we're putting all this information together, you had better have a polynomial that is behaving like this. It needs to be rising to the left and falling to the right. All right, let's get into the zeros. Okay, the next thing in part C says you need to list each real zero. So remember, that's a forewarning. In the upcoming sections, you're going to encounter zeros that have imaginary numbers. Okay, so we're looking for real zeros. And we're going to write down each one of those because the real zeros physically appear on the graph. The imaginary ones you won't see on a graph, okay? So we're going to list each real zero, state its multiplicity, and then remember, we're going to use the multiplicity to determine whether the graph crosses or touches the x-axis at each zero, okay? All right, so let's talk about how you would do this, okay? I haven't really explained to you yet about, how you come up with the multiplicity, so I'm about to do that now. Okay, all right, so remember, so far we've encountered up to degree 2, which is a quadratic function. So think about quadratic functions. How did we come up with their x-intercepts? Okay, well, for x-intercepts, and this is just in general, not just for quadratics, to solve for an x-intercept, which is a 0, you need to set y equal to 0. Okay, remember, f of x is y. Okay, so to solve for the zeros here, you need to set the f of x or the y equal to 0. Okay, and I'm going to use the broken down form here. Okay, so like I'm just writing this all out. Okay, this is what we need to solve for x. Okay, like I said, we've encountered up to degree 2. And so what we did for degree 2, to solve for something like this, we either factored or used the quadratic formula. Okay, now that we're higher than degree 2, there is no quadratic formula. So you have to rely on factoring. Okay, and like I said, this is already factored for us. Okay, it is something times something times something times something. You can see all the factors. Okay, so you've got one side equal to 0. It's already factored. What do you do now to get the intercepts? You're just going to take each factor, each of the things you're multiplying together, and you're going to set it equal to 0 and solve. And that's going to give you the intercepts, the x-intercepts. Okay? All right, so let's try this. We're going to take each factor, set it to 0, and solve. Okay? Our first factor is negative 1/4. Okay? So I'm going to do the work down here. Okay? So I'm going to take negative 1/4 and set it to 0. Okay? There's no x here. It doesn't make any sense. Negative 1/4 is just a number. It's negative 0.25. That doesn't equal 0. That doesn't make any sense. Okay, so we're going to scratch this out. Okay, basically, you only need to set the factors equal to 0. You only need to do that for the factors that contain an x. So since the negative 1/4 didn't contain an x, you can just skip it. All right, so we're going to move on to the next factor, 3x plus 1. Okay, I'm going to set that equal to 0, and I'm going to solve. So 3x plus 1 is equal to 0, okay? And I'm just going to subtract 1 from both sides. That's going to give me 3x is equal to negative 1. Divide both sides by 3. We're going to get an x-intercept of negative 1/3, okay? This is our first 0, okay? All right, so let's keep going, and then I'll come back and talk about multiplicity, okay? We have x minus 4, okay? I'm going to set that equal to 0 and solve. Okay, so here all we have to do is add 4 to both sides. We're going to get x equals 4, so that's going to be your next 0. Okay, and then if I look at the last factor, it is also x minus 4. It's a duplicate of the one we just had. Okay, so it's going to give you the same answer. Okay, so again, we get the x-intercept of 4. Okay, now in your table, you don't need to list it twice. Okay, that's where the multiplicity comes in. Multiplicity is basically how many times, the number of times you get each 0 as a 0. Okay, so like the negative 1/3, it came from the factor 3x plus 1. Okay, it was in the factorization one time. We only got it as a 0 one time, so its multiplicity is going to be 1. On the other hand, x minus 4, that particular factor was in the factorization once and twice, 2 times. So technically, we got the 0 of x equals 4 twice, so its multiplicity is 2. Okay, so basically that is what multiplicity is. It's the number of times you get the x-intercept or 0 as a 0. Okay, it's the number of times that the corresponding factor is appearing in the factorization. Okay, hopefully that makes sense. Okay, so now based on the multiplicity, we can decide what's going to happen on the graph at each of these x-intercepts. Okay, so the x-intercept negative 1/3, it has multiplicity 1. That's an odd number, so that means the polynomial function is going to cross the x-axis at that 0. Okay, at x equals 4, it has an even multiplicity of 2. So at x equals 4, our polynomial function is going to touch or bounce. Okay, whichever word you want to use. Okay, and I'm always going to give you a table this size, so don't feel like you have to fill out the whole thing. It's just there for however many spots that you need. Okay, so I can go ahead and scratch this out because that's all the zeros. Okay. All right, so we're moving on. Okay, we've done the x-intercepts. Okay, now we're going to do the y-intercept to get an extra point. Okay, so remember, to find a y-intercept, you need to set x equal to 0 and solve for y. Okay, so I'm going to go up to, the original function here, and I'm going to set x equal to 0. Okay, so we're going to get y equals, because that's your f of x, it's equal to negative 1/4 times 3x plus 1, that's going to be 3 times 0 plus 1, times x minus 4, which is 0 minus 4, times 0 minus 4. Okay, so everywhere I see an x, I'm plugging in 0, and now I'm going to simplify. This is going to give me negative 1/4 times, this is going to be 0 plus 1, that's going to be times 1, times 0 minus 4 is negative 4. Okay, and then another negative 4 if we simplify this. Okay, this is going to be negative times negative times negative is negative. Okay, and then if you simplify this, this 4 will cancel with this 4. Okay, so you're going to end up with negative 4 as your y-intercept. Okay, so this graph is going to go through 0, negative 4 as the y-intercept. Okay, next step in part E. Okay, we're asked for the maximum number of turning points on the graph. So remember the rule. the degree here is 3, so the maximum number of turning points is going to be the degree minus 1. Okay, so here that's going to be 3 minus 1, which is 2. So that's important because when you draw this thing, you can't have more than 2 turning points when you draw your graph. And remember, turning points are points where you change from increasing to decreasing or from decreasing to increasing. So we've completed steps A through E. In part F, we will use all of these results to draw a rough sketch of the function. Okay, so let's take a look at the grid. Okay, notice this is not the normal grid that I give you. I usually give you one where the X and Y axes are labeled with a scale, like they go from -10 to +10 in both the X and Y axes. So there's no scale here. So the first thing you're going to have to do is come up with a scale on your X and Y axes. Okay, you have to do that, otherwise I don't see where you're plotting your points. Okay, so let's take a look at this. First, let's start with the X axis. That is going to be dependent upon what your zeros are. Okay, so I have 2 zeros, -1/3 and +4. So I'm thinking we can get away with going by ones on the X axis. Okay, so I'm going to put a tick mark and say this is 1, 2, 3, 4, and so on. Okay, and then we're just going to have to approximate where -1/3 falls. Okay, let's see here. There we go. And then we'll have, if we look at the y-axis, our y-intercept is at 0, -4. So, usually when you're doing these polynomials of higher degree, your y values can get really big really fast. So you'll just have to make a decision based on the graph you're working with as to whether you want to use some kind of special spacing on the y-axis. Since my y-intercept here is -4, I think I'm going to go by 2's. Okay, but you could probably get away with going by 1's. Whatever scale you use, you need to label it. Okay, so I'm going to go 2, 4, 6, 8, and so on. Okay, and then the same thing in the negative direction. Okay, -2, -4, -6, -8, and so on. Just make sure you label it. Otherwise, I don't know what you're doing. Okay. All right, so that's your first step, is putting your scaling on here. Okay, so now let's see. We're going to have to put some points on here. Okay, first points. Let's deal with the X-intercepts. Okay, so we know we have one at -1/3 and we have one at +4. Okay, so here's +4. That's an X-intercept or a 0. Okay, and then -1/3 is going to be between -1 and 0, closer to 0. Okay, so let's go ahead and say -1/3 is about right here. Okay, and then we can put our y-intercept, it's at 0, -4. Okay, so based on my scaling on the y-axis, that's going to be right here. Okay, all right, so let's try to put this together. Okay, going back to the zeros, we have to adhere to the rule at -1/3, the graph is going to cross, and at x = 4, the graph is going to touch or bounce. Okay, so if you look at -1/3, you're supposed to cross here. So the way it's going, it looks like you're going to come through here and go down through the y-intercept. So you're crossing, you're going from, it looks like you're going to go from above the x-axis to below. Okay, and then at 4, you're supposed to bounce. Okay, so it's going to have to stay below, like if I'm at the y-intercept, you're going to have to stay below the x-axis, because if you come back up before you get to 4, then you'll have an additional x-intercept, and that's bad. Okay, so it looks like since we're going to have to bounce here or touch, it's just going to touch in this part. Okay, so I'm going to make a little cup here saying we're staying, below the x-axis here. Okay, all right, so let's see, we've got to have the correct end behavior. So we are supposed to basically rise left and fall right. So keep that in mind. Okay. So I'm going to go ahead and draw this in. Okay, you may have to do a couple of iterations to get it right, but remember you need to draw a smooth and continuous curve. There can't be any holes or gaps, no sharp corners, no cusps. Okay, so it looks like my graph is doing this. Okay, so I'm going to come down like this. Okay, so it's doing this. And then we don't know specific points, and that's okay. This is just a rough sketch. We need to catch the big ideas. Okay, so we're crossing at -1/3. We go through the Y-intercept, and then we don't know. We have to do something, and then we have to come back up to get through this X-intercept at 4. We touch or bounce there, and then we have to fall to the right. Okay, so this is a very rough sketch of what this polynomial function looks like. Okay, let's check it and to make sure we've got all the correct attributes. Okay, first thing in behavior, in our picture, are we rising to the left and falling to the right? Okay, yes, we are. If you look where my cursor is, we are rising to the left, we're falling to the right. Okay, next thing. Do we have each 0, and is it doing what it's supposed to be doing? Okay, so at -1/3, are we crossing? Yes. Okay, at 4, are we touching or bouncing? Yes. Okay, do we have a Y-intercept of 0, -4? Yes. Okay, turning points. Okay, is there no more than 2 turning points? Okay, so that's, places where you change from decreasing to increasing or from increasing to decreasing. Okay, so I'm going to trace the curve from left to right. Okay, and I'm going to mark every turning point with a red X. Okay, so I am falling here, so we're actually decreasing until right here. This is going to be a turning point. Okay, then we start increasing. Okay, and then here we start decreasing. Okay, for the rest of the time. Okay, so we have 2 turning points. So I'm going to write this here. This is a turning point. Okay, you can't have more than 2 turning points. Okay, or you'll have to redraw your graph. Okay, this is a smooth and continuous curve. And one other thing I'll mention, the domain here is all real numbers. Okay, domain of a polynomial has to be all real numbers. It does need to span the entire x-axis. So going up to the left, I'm putting arrowheads on the endpoints to say it continues in these directions forever. So again, this is a very rough sketch of our polynomial. This is what it looks like. As long as you have all the attributes that you found in parts A through E depicted in your graph, you should be good to go.